Hello and welcome dear students. Today we are going to discuss topic linear watershed characteristics. A watershed characteristic refers to the physical, hydrological and environmental attributes that define how a watershed behaves. Understanding these characteristics is vital for water resource management, soil conservation, flood control, hydrological modeling and watershed planning. Watershed characteristics are generally classified into 5 major categories. First one, morphological or physical characteristics. They include shape, size, structure and geometry of the watershed. Second is linear characteristics that include drainage network characteristics. The third one is aerial characteristics, that is surface features. Fourth one includes hydrological characteristics and the last one, that is fifth, that is socio-economic characteristics. Now, let us discuss one by one the linear morphological characteristics of the watershed. So, linear morphological or linear morphometric characteristics refers to the linear features of a drainage network such as stream number, length, order and ratios. So, they describe the geometry, structure and organization of a stream within a watershed. These characteristics helps us in understanding of runoff behavior, flood peaks, sediment transport, erosion rates and basin evolution and hydrological responses. Here are the classical linear parameters according to Houghton 1945 and Streller 1957, starting from first one, stream order. Stream order is a method of classifying or ranking natural stream segments based on the number of tributaries that feed into them. It is a key concept in fluvial geomorphology and hydrology, as it helps quantify branching complexity of a drainage basin, which in turn relates to the stream discharge, stream load and overall physical characteristics. The most widely accepted system for determining stream order is the Streller's stream order system. This is a modification of Houghton's system. The Streller assigned a numerical order to each stream segment in drainage network according to these rules. First order stream, these are the smallest unbranched permanent or intermittent tributary streams. They have no tributaries flowing into them. The source of the stream is always the beginning of a first order stream. Second order stream, a stream segment is designated as second order if it is formed by confluence of two or more first order streams. A second order stream can also receive drainage from other first order streams. The third order stream, a stream segment becomes third order when two or more second order streams joins. It can also receive tributaries from first and second order stream, but its order does not increase unless it receives a tributary of the same order. Higher order streams, in general a stream segment's order increases to the next whole number n only when it is joined by another stream segment of the same order. For example, two third order streams joining form a fourth order stream. Stream order is a fundamental parameter for analyzing the structure and functioning of a drainage network. Hydrology, generally low order streams have steep gradient, high water velocity and contribute primarily to local runoff. They make up the majority of the total channel length in a basin. However, higher order streams have gentle gradient, large channel width and depth and greater discharge. So, geomorphologically, stream order is directly related to the size of the contributing drainage area. Higher order stream drains large areas and helps to calculate various drainage basin morphometric laws, such as bifurcation ratio, which is the ratio of the number of streams of one order to the number of streams of the next higher order. This ratio is an indicator of geological control and texture of the drainage network. Now, stream number. Stream number refers to the total number of streams segments of each order within a drainage basin. It is one of the most fundamental linear morphometric parameter introduced by Horton. A stream segment is defined as a continuous stretch of channel between two junctions or from the origin to the first confluence. Stream number is the count of streams of a particular order within a watershed. So, Horton's law of stream number: the number of stream decreases geometrically with increasing stream order. This means first order streams are most numerous, while second order streams are fewer and the third order streams are even fewer. Highest order are least common. The relationship often follows an inverse geometric progression. This regularity, known as Horton's law of stream number, the stream number declines as the stream joins, they combine to form higher order streams, reducing total number. The stream number provide important clues about this. The first one is drainage network structure, the second is basin maturity, the third one is geological control, then hydrological responses and soil erosion potential. Then the third parameter is stream length. Stream length refers to the total length of the stream of a particular order within a watershed. It is one of the key linear morphometric parameter introduced by Horton to analyze the geometry, hydrology and geomorphic development of a drainage basin. Stream length helps in understanding of basin development, runoff and flood behavior, erosion and sediment transport, geological control. Horton in 1945 proposed stream length increases with stream order in a geometric sequence. If the ratio is constant, the basin shows orderly development and drainage is natural and undisturbed, whereas irregular ratio indicates structural disturbance, faults, resistant rock beds or anthropogenic modification. Factors that are influencing stream length are discussed as: first, slope. Steep slope shows shorter streams in the watershed, whereas gentle slopes reveal longer meandering streams. Second is geology or the rock type. Hard rocks show shorter, straighter streams, however, soft rocks are responsible for longer and dendritic pattern. Rainfall: high rainfall reveals more branching and longer stream network. Basin shape: elongated basins depict long main channels, but circular basin depicts comparatively shorter channels. Land use: deforestation or urbanization increases surface runoff and modifies microchannel length. Stream lengths are important for flood prediction as long as trunk stream delays peak discharge. Erosion intensity is dependent on stream length, which reflects the effectiveness of flowing water to detach and transport sediments. Watershed management used in designing the check dams, contour trenches, gully plugs and recharge structures. Stream length is measured using traditional methods and modern GIS based methods. The fourth parameter is mean stream length. Mean stream length is the average length of a segment of a particular stream order within a watershed. It provides a clear understanding of the geometric characteristics, flow behavior, structural control of the drainage basin. Streller in 1964 derived a formula where mean stream length is equal to total length of all the streams of a given order, number of streams of that order. Total stream length alone can be misleading because some orders may have many short streams or few long streams. Mean stream length gives a balanced normalized measure to compare different orders. Mean stream length helps to understand drainage texture, assess erosional stages of basin, deduce lithological characteristics, compare drainage maturity between different watersheds and importantly study stream evolution pattern, because higher order stream receives water from multiple tributaries, have longer flow path from major channels and represent mature stages of drainage development. This mean stream length also indicates a well developed natural and undisturbed drainage system, suggesting minimal structural distortion and stable geomorphic conditions. But if the pattern is regular, then it suggests structural disturbance, resistant rock types, tectonic influences and anthropogenic modification. The 5 major factors which can influence the watershed are slope, rock type, climate, drainage, density and the fifth, basin shape. Now, the fifth parameter is stream length ratio. Houghton in 1945 defined stream length ratio, which is a morphometric parameter that measures the ratio of the mean or the total stream length of one stream order to the next lower order in a drainage basin. It helps in understanding how the length of a stream increases with increasing stream order, revealing the basin's geomorphic, hydrological and structural characteristics. Stream length ratio indicates different parameters of the basin, like basin maturity, shows hydrological responses, reflects geological or structural influences. It helps in drainage pattern analysis, behavior of stream length ratio in most natural dendritic watershed, because higher order streams are fed by many tributaries, making them much longer. The sixth parameter is bifurcation ratio. Houghton in 1945 introduced fundamental morphometric parameters bifurcation ratio to express the ratio between the number of streams of one order and number of streams of the next higher order in the drainage basin. It is one of the most important indices used to evaluate the branching pattern of a drainage network, the degree of structural control, the maturity of the basin and the geological setting. Meaning and interpretation of bifurcation ratio. Bifurcation ratio shows how much the drainage is controlled by geological structures and indicates structural disturbances in watershed. High bifurcation ratio greater than 5 shows strong structural control and tectonic influences, whereas low bifurcation ratio between 2 to 3 depicts natural dendritic pattern with uniform rock type. Bifurcation ratio also indicate drainage texture and depicts how frequently streams branch. High bifurcation ratio shows coarse drainage texture and low bifurcation ratio shows fine drainage texture. The mature basin shows the branching network becomes consistent, resulting in a more uniform bifurcation ratio. Bifurcation ratio have two types, which are discussed as mean bifurcation ratio, that is computed by taking the average of bifurcation ratio across all stream order pairs, indicate degree of network organization. Now, another is weighted bifurcation ratio, introduced by Strehler to avoid distortion due to small stream segments. It gives a more reliable value by considering relative weightage of each stream segment. Now, the seventh parameter is drainage density. Again, Houghton in 1945 introduced fundamental morphometric parameter drainage density to express the total length of streams per unit area of a watershed. It measures how closely spaced the drainage channels are and reflects the runoff characteristics, infiltration capacity, relief, rock type and overall hydrological behavior of a basin. Drainage density is the ratio of a total stream length to the area of the basin. Drainage density values, that is less than 2 km per square kilometer, means low drainage density. It depicts high permeable soil, low relief, flat terrain, high infiltration, low runoff with well vegetated area. It also indicates youthful drainage stage. Moderate drainage density between 2 to 4 km per square kilometer area reveals moderate slope, moderate soil permeability, balanced infiltration and runoff. High drainage density greater than 4 shows impermeable rocks or soil, steep terrain, high runoff, low infiltration, arid or sparsely vegetated area. It also indicates mature and high dissected terrain in the watershed. The eighth parameter is stream frequency. Stream frequency is one of the important linear morphometric parameter used to understand the degree of drainage network developed in a watershed. Stream frequency is defined as the total number of stream segments per unit area of a watershed. It indicates how closely the streams are spaced within a drainage basin. Formula used for the calculation, whereas Fs is equal to stream frequency, Nu total number of the streams segments, A is the area of the watershed. Stream frequency shows the texture and the drainage intensity of a watershed. High stream frequency means more streams, which depicts high runoff, steep slopes and impermeable rock, but low stream frequency means few streams with high infiltration, gentle slope and permeable soil in the watershed. So, factors which affect stream frequency are climate and rainfall, slope and relief, geology and soil and dense vegetation. So, stream frequency indicates runoff potential, helps to assess erosion risk and sediment yield, used to determine drainage texture, reflects stages of landscape development and influence flood hazard and peak discharge in the basin. The ninth parameter is infiltration number. Infiltration number, introduced by Ferran in 1968, is a morphometric parameter used to express the combined influence of drainage density and stream frequency on the infiltration characteristics of a watershed. Infiltration number is a measure of the infiltration capacity of a watershed based on the product of drainage density and stream frequency. It indicates the opposing relationship between the infiltration rate and the density plus the frequency of the channels. Formula where If is equal to the infiltration number, D is the drainage density, Fs is the stream frequency. The infiltration number indicates how much water enters the ground versus how much becomes runoff. The high infiltration number shows low infiltration capacity with high runoff and higher erosion and flood potential. However, low infiltration number values represent high infiltration capacity and low runoff with better groundwater recharge. Thus, infiltration number is inversely related to infiltration, but directly related to drainage dissection. Infiltration number affected by number of factors like soil, permeability, permeable soil like sand or alluvium have low drainage density and stream frequency and low infiltration number. It represents impermeable soil with high drainage density and stream frequency and high infiltration number, whereas hard compact rocks show high runoff with high infiltration number, but weathered fractured rocks show low infiltration number. Steep slopes are responsible for faster runoff with high infiltration number, whereas gentle slopes show high infiltration with low infiltration number. Dense vegetation cover shows higher infiltration number with lower infiltration number, but sparse vegetation has more surface flow, which shows higher infiltration number. Heavy rainfall intensity also shows increased erosion runoff with high infiltration number, whereas low moderate rainfall shows better infiltration with low infiltration number. The infiltration number is crucial for understanding runoff and peak discharge. High infiltration number represents high peak flow, means flood prone basin. The third parameter is drainage intensity. This parameter, drainage intensity, was again introduced by Ferran in 1968 to measure the overall dissection of a watershed by expressing the relationship between stream frequency and drainage density. It helps in understanding how strongly a basin is dissected by stream channels, which affects runoff, infiltration and erosion. Drainage intensity is the ratio of stream frequency to drainage density in a watershed. It is a measure of how, for every unit of drainage density, how many streams exist. So, formula for drainage intensity, where Di is equal to drainage intensity, F is stream frequency, and Dd drainage density kilometer of stream length per square kilometer. So, the drainage intensity indicates how strongly the landscape is dissected. High drainage intensity value represents many stream relative to total drainage length with high terrain dissection and more runoff with less infiltration. Low drainage intensity values show fewer stream relative to drainage length with less dissection with higher infiltration and better groundwater recharge. Drainage density affected by many factors like geology and rock type. Impermeable rocks represent more surface channels with high drainage intensity, whereas permeable rocks show fewer channels with low drainage intensity. Soil type: clay soil depicts huge runoff with high drainage intensity, whereas sandy soil shows high infiltration with low drainage intensity. Relief or slope: steep slopes results fast runoff with high dissection and high drainage intensity, but gentle slopes have low dissection with low drainage intensity. Sparse vegetation cover have more surface flow with high drainage intensity, but dense vegetation has slowed runoff with low drainage intensity. The high intensity rainfall in watershed makes more channels result in high drainage intensity. However, low intensity rain results fewer erosional channels with low drainage intensity. The 11th parameter is length of overland flow. So, the length of overland flow is introduced by Houghton. It represents the average length of unchanneled surface runoff before the water enters a stream channel. It is a crucial indicator of infiltration capacity, runoff characteristic, erosion potential and basin hydrological responses. Length of overland flow is the average horizontal distance travelled by the water over the land surface before it becomes concentrated into a definite stream channel. It represents runoff movement before formation of rills and streams. The formula for the calculation given by the Houghton 1945 expressed it as, where LO is the length of overland flow, drainage density Dd, and length of overland flow is inversely proportional to drainage density. When drainage density is high, channels are very close and length of overland flow is shorter. When drainage density is low, channels are far apart, showing length of overland flow is long. Therefore, high drainage density represents short length of overland flow, meaning water quickly enters stream channels with high runoff. Low infiltration. Low drainage density represents long channel of overland flow, meaning water travels too long distances, as sheet or flow depicts higher infiltration. Several factors affecting the length of overland flow are slope and relief. Steep slope results fast flow with shorter duration, whereas gentle slope results slow flow with longer durations. Dense vegetation cover results in slow runoff with increase, whereas bare ground results in fast channeling with reduce. The soil permeability also shows variation, with soil characteristics like permeable soil results in higher infiltration within longer, and impermeable soil shows faster runoff and shorter duration. The area experiencing high intensity rainfall represents rapid rills formation, and shorter gentle rainfall results in sheet flow maintained with longer. The land use type also impact values, as urban surfaces show reduced, whereas agricultural forest areas show increase. This was all about the today's lecture. Hope you have enjoyed it well. Thank you very much for watching.